Hello everyone. In today's lecture, we're going to be looking at rate of change. It's an application of derivatives. Initially, we talked about determining a slope with the help of derivatives. Here we're going to see that derivatives also help us determine the rate of change of one variable with respect to another. For example, population growth rates, production rates, water flow rates, velocity, acceleration. Now, velocity and acceleration are used in the sense of describing a motion of an object, which is, say, moving in a straight line. And when we do these problems, we normally have a little convention that we either use a horizontal or a vertical line to represent the line of motion. Another convention is that if we move to the right or upwards, it's positive direction, or if we move to the left or downward, it is considered a negative direction. So let's start with average velocity. So you can think of this horizontal line as a road, and there's a car at time t. And after a certain time t, the car moves and is now at a new position. Suppose this position, say, was A, and after t plus delta t, it has moved to a new position B. So the function s, which gives the position, so this function s, which gives the position of an object as a function of time, is called the position function. So we're just looking at the movement of the car from position A to position B, and that is being represented by s over here. Now, if it says over a period of time, say delta t, so that means movement from t to t plus delta t, this object here is our car, it changes its position by the amount delta s. Okay, so I'm just representing the time. So I suppose this was s, then this is delta s. So it depends upon how you're looking at it. So when we say the object changes its position, so delta s is s of t plus delta t, that is position. Now this is b is my, think of s of t plus delta t, and where I started was a. Think of that. So the average velocity is given as change in distance over change in time. That's how we find the average velocity. So that's the formula. So let's go ahead, and also if you could think of this one, suppose suppose we're looking at the average function, change in distance over change in time over a time period. Suppose if it is, say, t and say t plus delta t, then the average velocity would be given as your s of t plus delta t minus s of t. That's what basically we'll be doing. I'm just writing it down much more, clearly here. And it is basically t plus delta t minus t. So that's how delta t comes about. That's basically how the formula is. Okay, so let's look at this example. So find the average velocity of the function f of t, which is given by t squared minus 7 over the given interval 3 and 3.1. So think of this as your t, and this is t plus delta t. So the average velocity is the change in the distance over the change in time. Your s of t, guys, is now f of t. So delta s is what? S of t plus delta t. Notice this one. So that's f of t plus delta t minus f of t over t plus delta t is 3.1 minus 3. Okay, think of this one. Okay, after that, it's just simple computation. So f of 3.1 is what? You plug it over here, 3.1 square minus 7 minus 3 square minus 7. You get 9.61, and minus 7 and positive 7 cancel out, divided by 0.1. And when you do the math, you get the average velocity to be 6.1. Okay, that's average velocity, which is kind of, think of this as your simple, sometimes we call it speed. That's the way you look at it. Okay, so now let's look at instantaneous velocity. Instantaneous means it is constantly changing. Think of that, the car example, as we are going. Notice when we're moving on a road, we're not having the same speed. It changes constantly. So that's kind of, we're going to look at this slide here. So in general, we say if S is a position function for an object moving along a straight line, then the velocity or the instantaneous velocity of the object is given as it's the differential of the position function, which is limit as delta t approaches 0 of s of t plus delta t minus st over delta t. It's like when you're moving on a road, as I said, if you look at your speed doesn't remain the same, the speed changes. So that's where right now, suppose you're driving, let's say 70 miles an hour, and after certain times it is now say 72 miles an hour. So those are the things we're talking about, instantaneous velocities in that sense we're talking here. So the velocity of the function, remember, is the derivative of the position function. It can be negative, 0, or positive. Okay, whereas the speed of an object is an absolute value of its velocity. Speed cannot be negative. Okay, we're going to look at an example. As I said, we'll look at the applications of derivative. We're going to look at a very classic example of the free falling object. So here are certain formulas if you recall from your physics class. If not, that's okay. Just remember that the position of a free falling object when you neglect the air resistance under the influence of gravity can be represented by this equation. S of t is minus half gt square plus v naught t plus s naught, where v naught and s naught, they are the initial velocity and the initial height. So here's a little typo. So this should be v naught. V naught is initial velocity, s naught is the initial height or the initial place where you're starting from, and g is the acceleration due to gravity. Keep in mind that in Earth, the value of g is approximately 32 feet per second or 9.8 meters per second. Sorry, again a typo here. Okay, let's look at an example. So it says at time t equal to 0, or in seconds here, a driver jumps from a platform diving board, which is 32 feet above the water. The initial velocity of the driver is 16 feet per second. Remember, it's coming down, so it's going to be so that's initial velocity when it starts is 16 feet per second. So the question is, when does the diver hit the water, and what is the diver's velocity at the impact? So remember, initial velocity, the driver is going to go first. You're not going to go jump straight. You're going to, if you're a swimmer, you know that you go a little jump ahead. That's the initial velocity, and that's why you're going to take the velocity to be positive. Okay, so using this position function, remember the formula we just had looked in previous slide. The s of t is minus half gt square plus v naught t plus s naught. We are given the initial height to be 32. And 16 is the initial velocity, and just plug in the numbers. Now the first question says, when is the diver, sorry, not the driver, it's a diver going to hit the water? So when the diver, remember this is the graph, so here's the diving board. That's how this, so this, when it hits the water, that means the s is 0. That means there is no more, that's what the meaning is. Hitting the water means s is 0. The distance has been covered, in other words. So it's negative 16 square plus 16t plus 32. You solve it. You can see the math here. We get t is minus 1 or 2. Now remember, t cannot be negative. T is time. It's an application. So we conclude that the diver hits the water at t equals 2 seconds. Okay. Now we're also asked this question, what is the diver's velocity at the impact? Okay, so to find the velocity, in other words, you need to know velocity is s prime of t. So it's negative 32t plus 16. Just plug in now. Remember, what is the diver's velocity when it hits the water? That's what the question is. That means after 2 seconds, that's when the diver is going to hit the water. So you just plug it over there. You find that it is minus 48 feet per second. Now, I'll just give you some practice problems. So here are the 2 slides having practice problems. A billiard ball is dropped from a height, and a ball problem, and then a rock is dropped from the edge of the cliff, which is 214 meters above water. So go ahead, guys, work on these problems. Thank you.